We're going to move from radicals to now chapter 9, which is all about quadratic functions. Today we're specifically going to talk about graphing these. Now, we've talked about a little bit about what a quadratic is before. Let's refresh. Quadratic is in the form of y is equal to ax squared plus bx plus c. If it's in this form, it's said to be in standard form. We'll find another form later. Each graph of a quadratic looks kind of like a U shape, and we call this a parabola. Or a quadratic. The parent function of every quadratic is y equals x squared, or f of x equals x squared. And there's a couple of unique features of all these quadratics. One is that they have something called a vertex, which is either their lowest or highest point. That would be right here. And they're also symmetric. In other words, you can fold them over a line of symmetry, and that axis of symmetry always goes through the vertex. These parabolas can either go up or they can go down. Now, turns out that we'll also have y-intercepts just like we would in any graph, and we'll have x-intercepts as well. Sometimes they're nice and clean and sometimes they won't be. One of the things about our axis of symmetry is that it can be found by taking a ratio of the opposite of b over 2a. And when we talk about b over 2a, we're talking about the b and the a in the quadratic function. Also, this y-intercept can be found, as in any problem, by setting x equal to 0. So if we set x equal to 0, the y-intercept is always going to equal c. Now, what really determines the shape of all parabolas and all quadratics is this a value out in front of the x squared. And if the absolute value of a is less than 0, the graph is going to get very wide. And if the absolute value of a is greater than 0, the graph tends to get much more narrow. Some more information regarding these quadratics is that if we know a is not equal to 0, because if a was equal to 0, we just have a linear function, bx plus c. But these parabolas will open up if the a value is greater than 0. Not the absolute value of a, but the actual a value is greater than 0, it opens up, and we say we have a minimum point at the vertex. And when we talk about the minimum value, remember, we talk about the y value is the minimum value. The x value is where it happens. Right? And then we know that if a is less than 0, we'll have a vertex in which a maximum occurs. And that's, again, the y value. The range of the function, or the quadratic in this case, is going to be equal to, if it were this type of problems, all y is greater than that minimum value. And in this case, the range would be all y's less than that value. So now let's go ahead and identify some things here. So here's a parabola or a quadratic. I don't have the equation for it, but I have just the general picture. We want to state the vertex, the line of symmetry, the y-intercept, and if the function is a maximum or a minimum. So the vertex is this lowest possible point right here, and that can be identified to be at 2 and negative 2. The line of symmetry goes through the vertex and is the line that the quadratic would fold over. So that's this line right here, and that would be equivalent to a vertical line, and vertical lines have the equation of x equals 2 in this case. We want to know what the y-intercept is. I can look right here, and I notice the y-intercept is also 2. And then we want to know if we have a maximum or a minimum. Well, this is the lowest possible point, so this is a min. And now we're going to state the domain and range. Turns out for all quadratics, the domain, since a quadratic will move forever to the left and forever to the right, is all reals. The range is everything from this point up. So we say y is greater than or equal to -2. Next, we're going to take and graph quadratics, and here's what we're going to try to do. The first thing we're going to do is we're going to find the x-coordinate of the vertex, or the line of symmetry. And to do this, we said we would take -b over 2a. The next thing we'll do is find the y-coordinate of the vertex. So basically, we're going to plug this -b over 2a into the function. So that's like f of -b over 2a. Then we'll identify the value of a, and that's the a and ax squared plus bx plus c, and multiply it to the y value. So a acts like a y multiplier. And then use that pattern and graph it from the vertex. So let's go ahead and do that. So here's our function, x squared plus 2x minus 3. To find the x value of the vertex, I like calling it v sub x. And this is also going to be the equation of the axis of symmetry. We take -b over 2a. The opposite of b is -2 in this case, over 2 times a. Coefficient in front of the x squared is a, which is 1. So that's equal to -1. So I have an x-coordinate of -1 to this quadratic. Then I'm going to find v sub y, or the y-coordinate of the vertex, by plugging this -1 into my function. So I have -1 squared plus 2 times -1 minus 3, which is going to be equal to 1 minus 2, which is -1, minus 3, which is -4. So I have a vertex of -1, -4. And go ahead and graph that right here. Next, I'm going to identify my a value and say a is equal to 1, and that's my y multiplier. Then I'm going to use my parent function, y equals x squared. If I graph that parent function of y equals x squared, I get 0, 1, 2, and 3. And if I square 0, I get 0. If I square 1, I get 1. Square 2, I get 4. Square 3, I get 9. This is actually the opposite of our radical functions that we just got done graphing. So this is the pattern that's going to exist from our vertex, or our new origin in this case. So from this point, I'm going to graph this pattern. So if I go over 1 and up 1, over 2 and up 4, and over 3 and up 9, I get 3 points on my parabola. However, that doesn't look like a parabola. Now, we also stated that wherever our vertex is, the line of symmetry goes right through that. So if I were to draw a dotted line all the way up, this is our line of symmetry, which means there will be points on the other side of this line at equal heights. So if I'm 1 away here, and I go 1 away over here, I get another point on the parabola. I'm 2 away here, if I go 2 away over here, there's another point. 3 away, and 1, 2, 3 away. So there's my parabola. And you'll notice, just coincidentally, that if I wanted to find my y-intercept, setting x equal to 0, I get -3, and hey, there's my y-intercept. Alright, so there's the graph. Range and domain. Domain, as we stated, is all reals. This has a minimum value, and that minimum value is -4. And the range is y is greater than or equal to -4. Let's do a few more examples. So here we have an a value equaling 3 and a b value equaling 6. And we want to find the x-coordinate of the vertex. So we'll take the opposite of 6 over 2 times positive 3. And we end up once again with -1 as our x-coordinate of the vertex. To find our y-coordinate of the vertex, we take and plug -1 into that function. So we have 3 times -1 squared plus 6 times -1 minus 2. And that will equal -5. So that means our vertex is at -1, -5. Go ahead and graph that. And that's also going to be, once again, our line of symmetry. So then we're going to take a look at our a value and graph our parent function. Zero, 0, 1, 1, 2, 4, 3, 9. But in this case, we have a y multiplier of 3. So I multiply 0 by 3, and I get 0. 1 by 3, I get 3. 4 by 3, I get 12. 9 by 3, I get 27. So this thing's going to get a little carried away. I won't be able to fit it on the graph. But we'll get the idea. So from this vertex point, I'm going to graph this x and this y right here. So if I move over 1 and up 3, I'll put a point. If I move over 2 and I move up 12 from there, and now I've kind of run out of room. So this is once again half of a parabola. If I take and draw my line of symmetry through my vertex straight up, I get that line that the graph will fold over. So then I can go back and say, well, if I'm 1 away on the right side from that line of symmetry, I can go 1 away on the left side and put a point. 2 away on the right, I can go 2 away on the left and put a point, and here's my graph. And again, I find a lot of the times, one easy way to check that I've graphed correctly is to check my y-intercept and see if I've done that correctly. Set x equal to 0, y is equal to -2, and what do you know, there's the y-intercept where it should be. So I've checked it correctly. All right? Domain, once again, all reals. Range, y greater than or equal to -5. So now you'll notice in this next example, A, the numbers are getting a little bit bigger, but B, our A value is negative. So that's going to change the direction in which this quadratic opens. B value in this case is 20. We're going to find the x-coordinate of our vertex by going -b over 2 times -2 in this case. That ends up being a total of 5. I want to find v sub y, the y-coordinate of the vertex. Again, I'm going to plug the 5 into that equation here. And we end up with 2. So I have a vertex of 5 and 2. Let's go ahead and graph that. So next, I'll take a look at my parent function. Once again, y equals x squared. So x and y. 0, 0, 1, 1, 2, 4, 3, 9. And in this case, my y multiplier is a -2. So I'll multiply by -2, and I get 0, -2, -8, -18. And again, I'll probably run out of room there. So let's go ahead and drawing my line of symmetry, which we also know comes right off of that vertex. And now we'll plot these points. I go over 1 and down 2. I go over 2 and down 8. And I've just run out of room probably. I don't think I'm going to get down 18 from there. I use this line of symmetry to find the other side of the parabola. So if I'm over 1 from this point to the right, I move over 1 from this point on the left. I'm over 2 from this point on the right. And I move over 2 from this point on the left. And there's my parabola. Now in this case, unfortunately, I can't really check to see if my y-intercept is correct. I can calculate it, but it's not going to show up on the graph that I've done. Our y-intercept, if x equals 0, is going to be negative 48. But that's not going to appear on what I've graphed, so I need to check another point. And I see a couple of points right here that look pretty nice. And I kind of want to keep them small, too. So this is, let's use 3 and negative 6 as a point to check. So I have to plug 3 and hopefully get out negative 6 in this equation here to check. So I have negative 2 times 3 squared plus 20 times 3 minus 48. And I hope I get negative 6. So this is negative 2 times 9 plus 60 minus 48. Negative 18 plus 60 minus 48. This ends up being 60 minus 66, which ends up being negative 6. And hey, what do you know? We'll plug in a 3 to get out a negative 6. That's the point, 3 and negative 6. I graphed this correctly. Make sure you check. That last test you guys took, where we had radical graphing, several of you didn't check your final graph. So, now we're going to take a look at a word problem. It says the height of an arrow can be modeled by this equation. So they basically give us a quadratic. Y is going to be the height after x seconds. And we want to graph this height of the arrow. So I'm going to just go ahead and sketch a graph. If I want dx, once again, I take negative b, which is 100 in this case, over 2 times negative 16. This isn't going to be very pretty, which is 100 over 32, or 25 over 8. And then I'd have to plug 25 over 8 into this function. And again, this is going to be somewhat of a calculator problem. I would probably make these a little cleaner on a test for you, so you could actually do it without a calculator, because if I have a calculator in my hand, all I really need to do is plug it into y equals and say go ahead and graph it. So we plug all that into our calculator, and I end up with about 160.24. So I have a vertex of, this is 3.125, that's this guy right here, and 160.24. So what that says is that if I were to graph this thing and I go over 3.125 and go up about 160.24, I get a dot here. Then I know that since the a value is negative, this is going to go down. So I'm just sketching this for right now. And we want to know at what height was the arrow shot. So at time 0, that will give us our height. So our time 0 is when x is equal to 0. If x is equal to 0, then y is equal to 4. So 4 feet is the height that was shot at. That also gives us our y-intercept. So if I were to take and graph this, let's do it a little more accurately. That number there is 4. And then we want to know what is the maximum height of the arrow. Well, the maximum height is this top right here. So the maximum height is just 160.24. That's the top of our vertex. That's all we got. Answer these questions and we'll discuss this a little bit more tomorrow.